Hi everyone. So as we discussed in our Zoom meeting this morning, um, I had several students ask for three types of problems. So this will be the first of the three that I'll address, which will be this one being determining the rate law from experimental data. The second will be using integrated rate laws, so either the first, second, or zeroth order integrated rate law. And the third one will be doing a half-life problem. So I've played a little bit with the font size, so hopefully everyone can see what is on my screen. If not, you can print out the practice problems found on EC Learn. So what I'm going to go through is just slowly how to attack this problem. As you have learned this morning when I'm using the writing tool, at least the way of the current setup that I have that is working, I might be able to troubleshoot in the future, but I cannot scroll down on the screen to write more. So occasionally I either need to interrupt the flow, or I might need to wipe the entire screen. So please keep that in mind. If that's the case and you need more time to catch up, either pause the video or just rewind a little bit. So to leave off where we started, so both sections got as far as to start comparing experiments 1 and 2. And we're going to put 2 over 1 based on whatever the larger rate is. We typically put on top. The math will still work out if you flip them. It makes our life easier if we put the larger rate on top. So what do I mean by that? So I'll take experiment 2, and then we'll compare it to experiment 1. So we remind ourselves what a rate law looks like. The generic rate law will follow this expression where we have the rate of the reaction, and it's going to be equal to some rate constant K, the concentration of reactant A raised to some power, reactant B raised to a power, and we're not limited by 2 reactants. It's just kind of a convenient way to write it, but we can add more if need be. What I think was giving people trouble with this particular problem is instead of having only 2 reactants like we did in our in-class examples, we now have 3. But this shouldn't freak us out too bad, because all we need to do is repeat the same steps just one additional time. And so it is unusual in 1102 to have a type of problem that can be solved by following the same steps, but this is one of those problems that follows the same steps every time. So actually, before I write out exactly our math, let's remind ourselves of our steps. So the first thing that we need to do is going to be, well, we already did that, but remember what a rate law is. So let's just jot it down again, and let's actually make it a little bit more specific. And we'll go to a third reactant, which I'll call C, and I'll raise that to the pth power. I know the letter O comes after N, but O looks a lot like the letter 0. So to avoid that, it's common to skip the letter O and go with the letter P. That's what I've done below. To make good use of screen economy, which is something I'm learning to do, instead of using the chemical symbols, I'm going to abbreviate each of the reactants as A, B, and C. So if we can remember our rate law, that means we're going to need to solve for a couple of variables. We'll need to know, in order, the exponent m, the exponent n, the exponent p, and then also the rate constant k. So we have 4 unknowns that we need to solve for. However, we need to ultimately keep in mind what our goal is for this problem, and that's to calculate the initial rate, and then it gives me a sequence of concentrations. We talked about this before, but I'd like to reiterate when I say, oops, I went to highlight the whole thing, initial rate, don't let that freak you out, right? So initial rate, if we look at a sketch, and we've seen this before, if we're looking at some kind of product grow in, right, we realize it's actually a curve. And what I mean by initial rate It's one way to kind of normalize the playing field, is that if all reactions are recorded at their initial rates where it really looks linear, then things are comparable. It's when you wait too long during an experiment that you start getting these weird curves and you start trying to find the derivative or the tangent that things can get a little messy. So when we do these types of experiments, typically what we stick with is what I have drawn here. Right? Here's our sketch of the curve. Our initial rate is that initial slope after the first, couple of time points. And that's what we're being asked to find. What is the rate initially if I have these concentrations that are given here? So that will be ultimately our final goal, is to calculate the rate with the given concentrations. That's our ultimate goal. So let's go in order of that. I'm going to wipe the whole screen now. What I want to do is put back, again, to remind ourselves, A, B, and C. And now what we're going to be attacking is, how do I solve for the rate law? K, M, N, and P. So we already did this during lecture. We're going to compare experiment 2 to experiment 1. And why did I choose those two experiments? Well, if we take a look, I'm just going to get rid of, well, that didn't work as well as I thought, so I'm not going to do that. But if we do look at experiments 1 and 2, we see at least one of the concentrations has been changed, but if we look at the other two sets of reactants, they remain constant. And we've already seen that if we have these constant concentrations, that's going to be a variable that's going to be able to drop out of an equation. So what do I mean by that? Let's write out the rate law expression for experiment 2. So the rate itself is 1.6 times 10 to the negative third. And just because I'm writing on the iPad, I'm trying to avoid using units because it takes up a lot of space and it can clutter what I'm trying to get across. You should include units when you're writing this out with a pen and pencil or paper, right? But I'm going to have to omit units for now for clarity. So we have our rate constant. We're going to have our concentration of A, but in experiment 2, that concentration is 0.20. It's raised to some unknown exponent m. Then we have our concentration of our second reactant, which is Br minus. For experiment 2, that's 1.0, and that will be raised to some exponent. And then we have our last reactant, which is H+, which also happens to coincidentally be 0.10, raised to an exponent of p, though. And we'll do the same thing for experiment 1. 8.0 times 10 to the negative fourth, even though it looks on first glance to be bigger than the rate of experiment 2, it's not. Check out the order of magnitude. It's actually about 2 times smaller. We'll have the same rate constant because we're talking about the same reaction at the same temperature, even though it's not explicitly stated. I'll always tell you if the temperature changes. So that K will remain constant. But the concentration of BrO3 minus in reaction 1 is 0.10. Be raised to the same exponent, and then we notice for the other two reactants, nothing changes compared to experiment 2. So what we can see then is a couple of variables fall out, because right now we have 4 unknowns. Well, K will fall out because they're identical, because we're talking about the same reactions under the same temperature conditions. We've just changed concentration, so K will be the same. 0.2 raised to the mth divided by 0.1 to the mth. Actually, I'm saying that, maybe I should be explicit. Remember, we're dividing those two equations. So that first term, that concentration of BrO3 minus, won't cancel, but we'll notice that the other two reactants do. 0.1 to the nth divided by 0.1 to the nth cancels. 0.1 to the pth divided by 0.1 to the pth cancels. So I'm going to switch colors so to trying to keep work organized. But if we do 1.6 times 10 to the negative third divided by 8.0 times 10 to the negative fourth, we'll get the number 2.0. Everything else cancels out. We're left with 0.20 to the mth over 0.10 to the mth. I also realize this is a weird color that I just chose, so if people do have issues seeing it on their end, let me know, and I'm going to whittle down which colors I can use. But I'm going to try to take advantage of the different color palettes I have to try and organize the work visually. But just let me know if things aren't working for you. So for this, it looks a little bit more complicated, but if we know some of our log rules, we can pull all the numbers within the parentheses since both are raised to the mth power. If we do that out, we'll find out 0.2 divided by 0.1 is the number 2.0. It looks like a 20. Sorry, I'm still getting used to the fidelity of this pen, this stylus. I got a better one, but it's still not working great with the software I'm using because I'm projecting from the iPad onto my computer, which then is recorded, so we're doing our best. So what we see here, I'm going to erase some of this to just simplify. We do all that math out, we're left with this equation. By process of elimination, m has to be equal to 1. I will let you know only for our class. So for our class, and I mentioned this in our Zoom lecture, that all exponents in rate laws will be whole numbers. So if you get something like 1.9, well, that's going to be equal to 2. If you get something 1.1, that's equal to 1. So things should be rounding to whole numbers. Just please keep in mind that in real life, you can have non-whole number exponents, though it is typically a rare occurrence. So what we're going to do, actually, I need to write this down physically, because I have to keep erasing things, but we do have that our first exponent, m, is equal to 1. So we need to iteratively go through this. The next thing, so if this is our m exponent to be with basically that reactant raised to that power, let's try to find now conditions in which I can find the second exponent that's going to correspond to Br minus. How I want to attack that is try to figure out which experiments will cancel out the contributions from this reactant and that reactant. So if I look here, if I compare experiments 2 and 3, the concentrations of Br3 minus are the same, and the same is the concentration for H plus, leaving Br minus to be the variable. And so those are the two we're going to want to compare. I take a look at the rates. Which one is larger? Experiment 3 is larger. Makes my math easier. I'll put experiment 3 over experiment 2. Other than making my math easier, there's no difference. You can do what you want, but I recommend this way. So we can write out our generic rate law. Again, I'm omitting units for clarity. So there's my rate of experiment 3 multiplied by whatever that constant is, k. My first variable is the BrO3 minus. Just so we can make it a little bit more clear, I'm going to get rid of some of these markings. But we see in experiment 3, the concentration is 0.20 raised to the mth, even though we know m equals 1. Doesn't really make a difference, at least in the math that we're doing. The second concentration for the Br minus is 0.15 to the nth, and then the concentration of H plus is 0.10 to the pth. We'll do the same for experiment 2. My rate is 1.6 times 10 to the negative third. My K is constant because I'm describing the same reaction at the same temperature. My concentration for my first reactant. My second reactant. Oh, did I mess this one up? That should be 0.15. This is 0.10. And then 0.10. We're going to divide both equations. cancel out like terms, kk, 0.2 to the mth, 0.2 to the mth, 0.1 to the pth, 0.1 to the pth. And let me see if I can figure a better color than orange. I'm going to go with purple to see how this works. So what we're going to need to do, I'm going to whip out my calculator so you can probably hear some noise in the background, but 2.4 times 10 raised to the negative third divided by 1.6 times 10 raised to the negative third, 1.5. So we already can see right away this is going to be a little tricky. But I take a look at what I have over here. These are the only variables that remain. 0.15 divided by 0.10 raised to the nth. So 0.15 divided by 0.1 is 1.5 to the nth. And hey, it's not that tricky. Sometimes you need to have confidence in where you're going. We now have both m and n as exponents of 1. So I'm going to wipe the screen again. I'll go a little bit quicker, maybe a little less talking, doing the last example. Try to do it on your own, skip ahead, see what the answer is. So the last thing I'll be doing, not the last thing, but one of the last things we'll be doing, is trying to find the exponent for h plus. So let's take a look. How do I get things to cancel? Let's see if we got this up. It's going to have to be 1 and 4, because I see 0.1 and 0.1, 0.1 and 0.1, then 0.1 and 0.25 are different. So let me set that up. Let's take a look at rates. 1 is smaller than 4, so I'll put experiment 4 on the top. The only reason I know how to do that so quick, I'm not even looking at the numbers, I'm looking at the order of magnitude. So I'll do experiment 4 versus experiment 1. Experiment 4, oops, can't see that, so I have to erase some of this. 4 is 5.0 times 10 to the negative third equals k, and that's going to be 0.10 to the mth, 0.10 to the nth, 0.25 to the pth. We're going to be dividing that by experiment 1, so the rate is 8.0 times 10 to the negative fourth. K is still the same, the concentration of my first reactant, second reactant, and third reactant. Take a look at what's canceling. KK, 0.1 to the mth, 0.1 to the mth, 0.1 to the nth, 0.1 to the nth. Let's do out this math. Again, I'm going to switch the color. I'll try purple again to keep things organized. So 5.0 times 10 raised to the negative third divided by 8 times 10 raised to the negative fourth. 6.25, and is going to equal 0.25 divided by 0.10 raised to the pth. Do that out. 0.25 divided by 0.1 is now 2.5 to the pth. And this is probably the hardest math we've seen. If you remember your log rules, which I hardly ever do off the top of my head, we can always fall back on our rule when we're doing, because this is based on literally atoms moving around, and atoms behave as individual units. That's actually why we have the whole numbers. Weird things can happen with the math, and that's how you can have fractions, but typically for us, we already said all exponents are whole numbers. So I'm going to recommend guess and check. So let's take 2.5 squared. Guess what 2.5 squared is? 2.5 squared is 6.25. I kind of ran out of room, but that means P must equal 2. So now we have M equals 1, N equals 1, P equals 2. We have now solved for all of our exponents. Still not done. We got a lot more to do. Right? This is a hard problem. This is literally asking everything we could do with this type of problem. All right. So let's write that down in the corner again. M equals 1. N equals 1. P equals 2. Step 2. Find K. So I can choose any of the 4 experiments I want, typically to not mess myself up. I just pick the first one so I don't have to overthink, so my eyes always go to where I expect it to go. So if I route experiment 1, I have 8.0 times 10 to the negative fourth Again, for this I'm going to be omitting units. We'll come back to those in a second. K that I'm solving for, my concentration of my first reactant raised to the first power, my second reactant raised to the first power because it's M and N, and then my third reactant, which is H plus 0.10, raised to the second power because that's P. So if I do 0.1 times 0.1 times 0.1 squared, what I end up with is 8.0 times 10 to the negative fourth equals K, 1 times 10 to the negative fourth. Got to isolate K, so 8 divided by that number, or 8 times 10 raised to the negative fourth divided by 1 times 10 to the negative fourth should give me 8. Hey, it does. Almost there. We have our quantitative value of K is 8, but we don't have the units. So there's two ways we can go about it. The quick way and the surefire way, which is the long way. So we found K. Now what we need to find K's units. So the quick way to do it is realizing the overall reaction order, which is M plus N plus P, which is 1 plus 1 plus 2, is going to equal 4. So we never really memorized a fourth order reaction, but we did know 0th is molar per second. First, can't spell, is per second. Second is per molar per second. Third is per molar squared per second, and we notice it was following this pattern. So I should be in per molar cubed. Sorry, it's really weird. Excuse me. Just my throat's getting dry from talking, that's all. Per molar cubed per second. So we could just do it that way, and we'd be totally fine and all set. I'll show you the long way to do this. The long way is going to be following our units, and this way will never lead you to the wrong answer. By definition, for us, rate is always molar per second because it's concentration change per unit time, right? We've looked at this a lot. That's our definition of rate right there. A being some generic compound. So that's my rate, has to be equal to those units. I'm trying to find the units of K. The concentration of BrO3 minus is represented in molar, raised to the first power. The concentration of Br minus is in molar, raised to the first power. And then we have our concentration for H plus, which is still in molar, but my P is now squared. So I take a look at this. That's not changing. K I'm still looking for. M times M squared. M to the fourth. Do some of that math out. Divide both sides by M to the fourth. That's M over M to the fourth per second. These are the units for K. Take a look here. One of the M's falls out. And we get exactly what we did in the last example. 1 over M cubed per second. So per molar cube per second would be the way you pronounce that. Oops, let's make it a capital M. So we have per molar cubed per second will be our units for K. Let me just write this down real quick so that I can wipe the screen and I don't lose where we are. Almost done. I know this is a super long problem, but it's literally covering everything that I could ask you. We are now all set to finally answer the final question. What is the rate given the concentrations provided? So I'm solving for rate this time. I know what my K is. It's 8.0 times 10. Oh, no, it's just 8. 8.0 multiplied by the concentration of BrO3 minus, which is 0.30 raised to the first power, because M equals 1. Concentration of Br minus is 0.050 raised to the first. Why? Because N equals 1. And then my concentration of H plus is 0.15 raised to the second. Why? Because P we already found was equal to 2. Let me clean this up a little bit because it looks a little messy. But that's the math that we're doing, so let's do that out. I always start kind of with the more complicated stuff, so 0.15 squared, I'll start with that, multiplied by 0.05 times 0.3 times 8. 0.0027 with sig fig, 2.7 times 10 to the negative third. Rate is always in molar per second. Or if it's a little bit different, always go back to the chart. It'll tell you exactly what units you have. That's how we finish off a problem like this. It was complicated, I know, but this literally was designed so I could test you to the ultimate end on this. It could get harder. I could somehow have 4 things reacting, but if you can do this, you are in good shape for the quiz. At least, I will guarantee you will have one of these problems on the quiz. So hopefully you're in good shape for that. Alright, I'm going to stop now because we finished the problem. So I'm going to erase everything. Hopefully that helps clarify from some stuff. And also reminds people where we were. It's been a long time since we've talked about all this, so it's probably good to review. All right, so that will be the end of this practice problem. Again, I know it's long. You won't see something this long on the quiz, but like I said, this is about as hard as it can get.